Today we will talk about network models. We're still in our operations research course. Network models is basically modeling any real life network in terms of a certain set of equations and predetermined definitions to be able to solve those networks. A network could be a transportation network, a certain vehicle moving from point A to point B. It could be delivery services, it could be an airplane trajectory, it could be a production line, pallet motion through that production line, and all those details. So let's learn more about the network models within the operations research. So the network, if you want to define it, it is two sets of symbols that's containing nodes and arcs. So first we define a set that we call it V, that is a set of points. It can be called V standing for vertices. The vertices of a graph or a network is called a node. So here, as you can see in the figure, number 1 is a node, number 2, number 3, and number 4. And going from number 1 to number 2, that's called a path. Let's move for extra more definitions. An arc is consisting of an ordered pair of vertices that represent a possible direction of motion that may occur between two vertices. So an arc is a motion trajectory between two vertices or between two nodes. So when you go from point 1 to 2, that's a path. But if you go from point 4, which is a node 4, to node 3, so this is an arc. If you have a sequence of arcs so that every arc has exactly one vertex in common with the previous arc, that we call as a chain. So if you go from joint 1 in a line to joint to node, from node 1 in a line to node 2, in a line to node 3, in a line to node 4. So 1, 2, 3, and 4 are called as a chain. Now the path is a chain in which the terminal node of each arc is identical to the initial node of the next arc. So again, the path is a chain in which the terminal node of each arc is identical to the initial node of the next arc. So if you go from 1 to 2, then again you go from 2 to 3. So that's a path because you used node number 2 to be identical for the first arc and the second arc, or for the first line and the second line. So if we go from 1 to 2, from nodes 1 to 2, 2 to 3, and 4 to 3, that is called a chain but not a path. So 1 to 2, 2 to 3, then we go 4 to 3. That's a chain. It's a continuous line of actions between nodes, but that's not a path because path should have the same direction all over the way. If you go 1 to 2, then again 2, notice that you have 2. Wherever the first chain ended, the second chain started, or the first path ended, second path started. 2 to 3, 3 to 4, that's a chain and a path. So you go 1 to 2, then 2 to 3, 3 to 4. That's a chain between 1 and 4, and that's a path from 1, 2, 3, and 4. The path 1 to 2, 2 to 3, 3 and 4 is a way to travel from node 1 to node 4, so that's a path. If that line you're drawing between joints or between nodes is telling you how to go from point A to point Z, then that's a path, in short story. Now, as a follow-up for one of the most important topics in the network models is the shortest path problem. That's why people are studying this kind of science. Let's say you have a company, and this is FedEx company, a company to ship stuff to people, or Amazon. and you want to go from point A to point Z in the shortest path. Now you care about how long, either in terms of time or in terms of distance, does it take from point A to point Z, and what are my options? So those kind of things are translated into money and into cost. So the shorter your path, the less your cost. So that's the importance behind this kind of science. So if we assume that each arc in the network has a length associated with it, then we suppose we start at a particular node, let's say here node A, then the problem of finding the shortest path, or the path with the minimum length, from node A to any other node in the network is called a shortest path problem. If I tell you what's the shortest path, or what is the fastest route going from A to E, it doesn't matter if you pass through B or C. Sometimes there's constraints. You need to pass through B and through C before you reach to E. In this case, there's no constraints. What's the shortest path? If these numbers representing the distance in miles, then what is the shortest path? Then you can do your calculation until you find the shortest path, which I can tell directly it's from A to C to E. In this way, you are passing only 5 miles. So that kind of logic is being followed. Same kind of algorithm, I believe, is applied through the navigation systems that are sold in the market. Navigation system through our mobile phones, or through all software tools or software options provided in the market, following similar kind of algorithms to find the shortest path for the customer. So if we take an example, assume that we have a shipment company that is sending a shipment from plant 1. Company have a plant called plant 1 in here. They need to ship their product to city 1, which is node number 6. So you are moving from node 1 to node 6. That's a shortest path problem. What you're asking is, if you know all the miles and distances between all the available nodes, then what is the shortest path and the fastest route, which means in other words, going from node 1 to node 6. But you still need to pass through relay substations, which is nodes 2 to 5. So nodes 2 to 5 need to be passed. Now, as you see in these numbers, these representing the miles. So what is the shortest path in this case? So you can say either I go from node 1 to 2 to 5 to 6, or from node 1 to 3 to 5 to 6, or from node 1 to 2 to 4 to 6. Then you see the shortest, while considering the constraints in mind that you need to go through relay substations nodes 2 to 5. So in this case, substations 2 to 4 are 3 miles apart from each other, and the shipment can't be sent between substations 4 and 5. There is no line or path going from 4 to 5, but the company still want to ship the shipment from plant 1 to city 1 in this case. So find the shortest path. So if you go from here 4 miles to joint 2, 2 miles to 5, and 2 to 6, that's total of 8 miles. If you go from 1 to 3, 3 to 5, 5 to 6, that's total of 8 miles as well. So it doesn't matter in this case if you go from 1 to 2 to 5 to 6, or from 1 to 3 to 5 to 6. They are the same distance. But if your constraints are changing, you can go from 1 to 2 to 4 to 6. In this case, you have 9 miles, which doesn't, it's not feasible and doesn't make sense to go that route. So whatever route you choose, other than route 1, 2, 4, 6, and following the constraints, will be a feasible route in this case. That's it about network models. Thank you.